Swayam Prabha. Digital India. Educated India.
Good morning. We are going to continue our discussion on various spray nozzle designs. Towards the end of the class, we had looked at two sort of designs of spray nozzles. One that is just a through hole through which you squirt liquid that is pressurized, a design that is commonly used in diesel injectors, and another which is more widely used design called the simplex swirl atomizer. This simplex swirl atomizer is fairly simple in its construction. Essentially, a set of tangential passages bring the fluid into a chamber called the swirl chamber, and that swirl chamber has a converging passage in which the swirl action is accelerated. So, the swirl velocity is accelerated, and that acceleration causes the liquid to exit the spray nozzle by just forming into a thin film that is sticking to the walls of the orifice. And the big advantage of this design, as we discussed in that class, is that the size of the film that is formed is what is going to determine the drop size later on, not the size of the orifice. So, I have now sort of decoupled machining practices from fluid mechanic performance of the spray nozzle, which is always a good thing. Okay. What we are going to do just briefly is to look at one of these spray nozzles in action. We are going to look at a video of a fairly common simplex swirl nozzle from a water spray container. We will see in just a moment. Let me start to play the video. This was captured at 10,000 frames a second and is being played back at 30 frames a second. Let me pause the video here. Now, what you see over here is the tip of the spray container. What you see coming out is a conical sheet of water, and the conical sheet of water, when I play this, you will see, is not just a steady cone. It is sort of flapping, it has got a temporal oscillation to it, it is flapping and is undergoing let me pause the video. So, is undergoing a certain kind of breakup process. So, this flapping liquid sheet exiting the swirl spray nozzle is what is responsible for its breakup, and as you can see, the sheet is breaking up right around the region where my mouse is pointing, and further downstream you essentially have drops that are moving downstream. Okay, so, this is an instance where the sheet thickness is not very obvious in this film, but the sheet thickness is much smaller than the orifice through which the sheet is exiting, and that sheet, because of its unsteadiness, is responsible for the sheet itself breaking up into what looks like rings. You can see the oscillatory motion of the sheet. Now, I want you to now go back and make some observations Now, if you look at this, there is the sheet, the conical sheet exiting the nozzle is not steady and is flapping, and this flapping motion is due to the the swirl action which is causing the liquid sheet to expand outwards, and the very fact that fluid mechanically this kind of a velocity profile is unstable. We will look at that as we go along as well. Now, this flapping liquid sheet causes the liquid sheet, in this particular instance you can see evidence that it is sort of breaking up into rings, and the rings themselves are further breaking up into drops further downstream. So, if you will imagine for a moment a sheet like this breaking up into rings, the ring diameter, or if you will, it is like a toroidal ring, the torus diameter is now going to be determined by the film thickness. It is going to be on the order of the film thickness, and that film thickness being small by accelerated swirl is naturally going to be responsible for smaller drops downstream. Okay, so, that is the mechanism by which drop size is controlled in a design like this. Okay. Now, another feature to observe here is that, well, again it is not very obvious here, but the fact that I have spread the liquid out into a swirling liquid sheet is going to naturally cause all the drops to be concentrated in a donut of sort with a hole in the middle where there is no concentration of fluid. Now, there may be applications where that is good, where I want all of the drops to be only on the periphery, I do not want anything in the middle. But in instances where I want a uniform distribution of drops, for example, a paint spray, when I paint a wall, I want to have a relatively uniform coating all over. I do not want a thick edge on top and bottom of the spray and a sort of a less dense coating in the middle. I do not want that. So, I would rather prefer a full sort of a more uniform coating of the spray paint, and for that there are designs that have evolved which are sort of evolutions from the simplex nozzle. The simplex atomizer is like I said, it is one of the most widely used, and many of the other designs you will see today are all based on the basic simplex concept. Okay, so, one variant of the simplex concept is what we are seeing here in this schematic. The liquid comes through the through this sort of an annular passage, and because of these veins these veins cause the liquid to be introduced into this region through with a certain kind of a swirl action. Okay. So, you create a natural swirl inside this chamber that is going to be oriented in that direction, except you are also introducing some liquid directly through the middle through a center orifice of kind. Okay. So, not only is this going to create a swirl action, but it is also going to create some liquid coming straight through this way. So, the resulting spray is going to be a combination of a pressure swirl and a pressure jet atomizer, and so therefore, this is essentially to control the spray pattern coming out of the nozzle. The pattern is an indication of whether the drops in the spray are distributed in a hollow cone or in a solid disc like distribution. Okay. So, in this particular design, it is more likely that you are going to have drops in the middle. Now, because of the way the simplex part of this nozzle works in relation to the pressure jet part of the nozzle. So, this is more like a pressure jet spray, and this part is more like a simplex spray. Because of a combination of these two, the drop sizes coming out of the pressure jet are going to be generally larger than the drop sizes in the simplex spray. So, while I have ensured that there is sort of a more uniform volume drop volume distribution, that drop volume in the middle of the spray near the center line of this spray is going to be distributed into larger drops in comparison with the drops on the periphery of the spray. So, this is sort of a by result of this kind of a design. There is really no way around it as far as this design is concerned. Okay, but we have at least overcome the problem of having nothing in the middle, no fuel or no liquid in the middle. Okay. The next kind of design is again an offshoot of the simplex nozzle, and this particular design is, it simplifies a few different aspects of the simplex nozzle in by making the passages fairly large. This is again a schematic where the liquid is injected through the middle through this. What we are seeing here is sort of a cut section of the nozzle itself, and there is an insert. This is typically called a swirl insert, that is responsible. It is sort of like two fans, two vanes in the that are oriented as an X. So, the liquid that comes up the first vane is going to cause a swirling action in this direction. The liquid that comes up this vane is going to cause a swirling action this way, and by engineering a small passage here, we can cause some fluid to come directly down the middle as well. Okay. That column of fluid that comes down the middle is also going to be is going to be in the vicinity of this swirl vortex that is formed inside the simplex nozzle. As a result, it is also going to be a swirling column of liquid that is going to come out in the form of a spray. Okay. Again, this is a solid cone design, but I can, by taking this Y, so I am going to try and draw a schematic of this. The fluid that comes up this way is going to cause it to swirl this way. The fluid that comes up the other way is going to cause it to swirl this way, and that causes a swirling action in the swirl chamber. So, the drop size in this case is again determined by the angle of this swirl insert. In some sense, that angle is going to determine the magnitude of the swirl velocity in relation to the axial velocity, and that essentially determines like the swirl momentum flux. That swirl momentum flux is what is responsible for the degree to which the film is sticking to the wall. Okay. One of the features of all of these nozzles is that I have one fluid inlet that brings fluid into the nozzle, and all the fluid that enters the nozzle is sprayed. Now, as I increase the supply pressure, so if you go back to the simplex design for a moment, as we increase the supply pressure at this point, which is the same at all the 4 inlets, as we increase that supply pressure, you are likely to see that the flow rate through this nozzle goes up. Okay. It is because the geometry of the passages remains the same. As the pressure goes up, the flow rate through the nozzle goes up. As the flow rate goes up, because of the nature of the geometry, the swirl velocity also goes up. So, there is a range of operation where increasing the pressure increases the flow rate without adversely affecting the drop size in the spray. That is usually the range where simplex nozzles are employed. But because of the nature of these features, so essentially if you will imagine, these are like restrictions, they are like fluid mechanic restrictions. People have found over many kinds of designs that in a typical simplex spray, Q goes as the square root of delta P. I use the symbol delta P for supply pressure. It is essentially the difference in the pressure between the actual absolute pressure at which the liquid is supplied and the pressure into which the spray enters. Assume for a moment that the spray enters pure ambient conditions. So, delta P is the same as the gauge pressure that at the entry to the nozzle, and this relation that the flow rate goes as square root of delta P is sort of empirically observed in many different kinds of nozzles. Actual data shows that this is the exponent is not exactly 0.5, but close to 0.45. So, Q goes as delta P raised to the power 0.45, that is again over a wide class of simplex nozzles. There is a problem with this square root kind of dependence, that if I increase the supply pressure by a factor of 4, I only get a factor of 2 change in the flow rate. So, if I want to double the flow rate, conversely I have to increase the supply pressure 4 times, which is usually quite difficult to do. Just to again get some order of magnitude estimates, most simplex spray nozzles operate at pressures between about 2 bar to about 7 bar. So, like for example, your spray water can that we saw just a moment ago is probably the nozzle part itself is operating at a pressure right about 2 to 3 bar. Okay, to go up from about 2 bar, if I have to double the flow rate coming out, I have to go up to 8 bar, which is prohibitive in many applications. So, but on the other hand, I want to be able to modulate the fuel output coming out in the form of a spray. I want to be able to control what comes out, the mass flow rate of the, let us just say, fuel that comes out of this spray nozzle. Because for one simple example is, let us take a process furnace. So, I have a boiler in which there is an oil fired burner. So, we are spraying some kind of a petroleum based oil into a combustion chamber to create heat for use in a process heating application. Now, when I start up this process cold on a Monday morning, I require a high throughput of heat and consequently a high oil flow rate. But after I have heated up the contents of this let us just say boiler or the process heater up to a certain temperature, I only want to maintain it at that temperature. I only want to add as much heat as required to overcome losses around the losses to the ambient environment. So, the startup requires a very high flow rate, the maintenance of that temperature only requires what is often called trickle heating. So, how do what sort of a spray nozzle can I use that will give me a certain flow rate for startup conditions and something like a tenth of the flow rate during normal operating conditions. This kind of a problem is also encountered in aircraft, where at the takeoff point the pilot is running the aircraft full thrust, which is when all the atomizers are firing at their highest flow rate. But when the pilot is only cruising at some high altitude, you do not require full thrust, and so the spray nozzles have to now scale back and operate at a much much lower flow rate condition, but at the same time produce a good spray quality in terms of drop size. Okay, so here is a design that does that. This is called a spill return atomizer. If you will consider this, essentially there is an inlet. So, the inlet is at some pressure at some supply pressure, typically let us say 7 bar. 7 bar is about 100 psi, 10 bar is about 150 pounds per square inch. So, these are all units that are used commonly in the spray industry. So, let us just say the supply is at 7 bar, and this is supply going into a conventional simplex nozzle. So, this part here is a regular simplex atomizer. It would exactly be a simplex atomizer, but for this one hole that brings the fuel back out of this swirl chamber called the spill return. Now, let us see what this does. Let us say I will take a situation where I have a valve on this line. If that valve is completely closed, then whatever supply goes into the swirl chamber has to come out in the form of a spray. If I partially crack the valve open, then a part of the flow rate is now allowed to come back to a supply tank of sorts, and by controlling the opening on this valve, I can control the actual flow rate of the spray coming out of the nozzle, the flow rate of the spray coming out in the form of drops. Now, typically again from observations, what we find is that between the two extreme cases where the valve is completely closed and completely open, the actual flow rate of the fuel going into the swirl chamber does change. Okay. When the valve is completely open, there is actually more fuel going in. So, even though you have less spray coming out in the situation where the valve is completely open, there is more fuel going in through the inlet line, okay. But most of it is returning back to the through the spill line into the tank. Okay, so, by opening the valve completely, we increase the flow rate coming into the nozzle, but decrease the flow rate coming out in the form of a spray. It is a little counterintuitive, but it is a very elegant design to get a ratio of highest to lowest flow rates by almost a factor of 10. Okay, a factor of 10 is not too difficult to achieve in a design like this. Okay. So, if I take the situation where the valve is completely closed, it is just a regular simplex spray nozzle. When the valve is completely open, you have a high flow rate coming into the swirl chamber. Because of that, you have a high inertia associated with the swirl. So, actually as the valve is opened, the flow rate coming out of the swirl nozzle goes down, but since the angular momentum flux is higher than when the valve is completely closed, the drop size is lower. Okay, so, we will just write this down. So, if I take a reference situation where the valve's position is completely closed, inlet flow is, let us say, Q, the spray flow is also equal to Q. When the valve is partially open, the inlet flow rate is greater than Q and the spray flow rate is less than Q, and if D is the drop size, this is less than D. So, as you open the valve, the spray flow rate decreases, and because you are putting in a higher angular momentum through the higher flow rate, because the inlet flow rate is greater than Q and all of this inlet flow rate is coming in through tangential passages, but the flow going out is not taking back any of that angular momentum, it is only taking out linear momentum. So, you introduce the flow with some angular momentum, but what is coming out through the spill line is only in some sense linear momentum flux. So, all of the angular momentum flux that came in with the higher flow rate is now entirely with the spray alone, that causes a lower film thickness and smaller drops. It is a very nice design to actually get many different design objectives achieved. Okay. Now, like I said, a factor of 10 ratio between the highest and the lowest flow rate is quite possible, not difficult at all. Now, what is, I mean, nothing in life comes for free, there is an overhead. In that, let us say if Q is my completely closed condition flow rate, and if I take the fully open condition, let us just say I have the inlet flow rate is now greater than Q and the spray flow rate is a tenth of Q. So, this is assuming a turn down ratio on the order of 10. Turn down ratio is defined as the highest flow rate possible in that nozzle divided by the lowest flow rate. So, when I have a factor of 10 lower flow rate coming through there, this inlet flow rate is, let us say, is typically about 3 times is a factor of 3 higher. So, I am putting in 3 times the flow rate to get a tenth of the flow rate. As opposed to this, if I had a simplex nozzle that was designed to spray Q by 10 at with a supply pressure of 7 bar, that would use much lower energy. So, essentially the amount of energy that I am inputting now at this fully open condition is 3 Q flow rate at a supply pressure of 7 bar. That energy is clearly greater than putting in Q by 10 flow rate at a supply pressure of 7 bar. So, it is like the pumping power required is much higher in this case, but then in return for that you gain the flexibility of being able to control what the spray flow rate is on the fly without needing to do anything to the pump and the pumping system. By opening and closing a valve, we can control the throughput coming out. Again, just to sort of complete this discussion, since the angular momentum flux is higher in the fully open condition, the cone angle is now bigger, because you have a higher swirl velocity per unit flow rate. The cone that comes out of the liquid spray nozzle is now going to be of a wider angle. So, typically the spray angle increases as you go through this process of opening the control valve. So, these are all designs where our intention is to create, as you see, axisymmetric sprays. All of these designs thus far are only intended to create sprays which have a general axis over about which you expect the spray to be symmetric. Okay. Now, there may be many applications where I do not want a symmetric spray, I want something that is more like a flat spray. So, typically if I am in the business of washing the sides of a building, let us say, I do not want an axisymmetric spray as much as I would like a fan spray. Okay. So, what I want is a flat spray that I can use to just clean dirt on the off the side of a wall. Okay. This is one such design. Now, the simplest way to imagine this is that again you have liquid coming in on one side, the liquid goes through, comes out in the form of a jet here, and this is basically a profile to spread this jet coming out on this side into a film. So, the simplest instance that you can imagine is, let us say I take a faucet, a water jet coming down, and I hold a spoon, a regular old kitchen spoon, and I allow so, as this liquid jet falls on the spoon, you can easily see how it spreads out into a fan, and the fan breaks up just like the conical, you essentially create a high speed fluttering fan of liquid sheet. It is essentially a liquid sheet that is fluttering, and this fluttering liquid sheet is going to break up further into drops. That is the design for of this flat spray, so called flood nozzle. It is called a flood nozzle because it is one of the nozzles that gives you a very high flow rate with reasonably good drop size. Reasonably good is a few hundred microns is very achievable in a design like this. Okay. And the basic principle is exactly the same as water falling on top of a kitchen on top of a spoon in a kitchen faucet. And what you create is a spray that is sort of like a fan. The next design is also intended to create a flat spray, except it is slightly different than the flood nozzle design. Okay. The outside looks something like this. I am going to try and see if I can draw a cut section through here. When I take a cut section through this section here, this is what it looks like. What you essentially have happening here is that the liquid goes through this central part and is made to converge at this section somewhere on the inside over here. So, if you will imagine the liquid sort of converging from two sides, and on top here if you look at this view from top, that is essentially like an eye of a cat. So, this view is going to create an orifice that looks sort of like the eye of a cat. It is oriented in and out of this, of the plane of this board. So, these two liquid jets, if you will, converging on to near the cat's eye orifice essentially causes this liquid to be spread into a thin film, and that thin film is now going to break up and create a fan spray in this direction. So, in the other plane, if this is my cat's eye, I end up creating a fan spray. Most pressure washers that you see, that are used to use that use high pressure water for cleaning, use a design like this. So, anywhere that you require a flat fan like spray with a reasonably low drop size. So, you do not want something that is completely atomized, because the intention of these applications is to actually have drops impacting the substrate and cleaning dirt or cleaning grime. I do not want to create a mist that just diffuses into the air. So, I in fact, in an application like this, I do not want very good atomization. I just want drops to be distributed into a fan, where the drops themselves are large enough to ballistically carry their momentum all the way to the substrate. Okay. So, some of these designs are intended to show you that good spray quality does not always mean extremely fine atomized spray. A classic example is a firefighter. When a firefighter uses a fire hose nozzle and shoots a cylindrical jet of liquid, let us say towards the second floor of a building, you do not want any you do not in fact want any atomization. For all practical purposes, it is a pressure jet, but I want the liquid to remain intact and be carried all the way to the target, which could be on a second floor. Now, this requires a certain kind of nozzle design that keeps it from getting atomized. Okay. So, typically you will see fire hose nozzles are extremely streamlined to prevent the introduction of any kind of disturbances to the cylindrical liquid jet, and you create even at a relatively high Reynolds number a fairly laminar looking jet. So, the surface is devoid of many perturbations, and that is the starting point for this jet to remain intact all the way to your target. In the process, if this jet were to break down and give you atomized quality jet, so if you create drops, you are more likely to not reach the target substrate, because these drops, the same volume of liquid distributed into a collection of drops, is going to have a higher drag force on it, which is going to prevent it from reaching the target. So, these next few examples are intended to show you that there are many, in some instances, competing design interests that are achieved through these designs. Okay. So, this is again another instance of a non-axisymmetric geometry, where you want some atomization because you want the liquid to be distributed, but you do not want extremely fine spray. You do not want an extremely fine spray. Okay, let us come to this in a little bit. I want to first talk about typical air mixing atomizers. Up until now, the source of energy, remember we said there are two things that the spray nozzle does. One, it brings the liquid in contact with a source of energy, that is essentially the objective of a spray nozzle. The source of energy in all of the previous designs was the liquid inertia itself. So, the liquid moving fast in a stagnant environment of air, okay, was the source of energy. We are now going to look at some designs where air in some compressed form is used as the source of energy. Okay, so we will start to look at this first design, where if you will imagine liquid entering through these annular gaps and coming out. So, this part here, so these are tangential injectors, injection slots, so this part here is just like a simplex nozzle. So, I have liquid being injected through a pair or some number of tangential slots, okay, and these tangential slots cause a little swirling action in this region. I have some sort of a spillover of this liquid sheet. On the outside, we have air coming in, again remember this is sort of an axisymmetric design. So, this air is also being fed in through here, and this indicates a swirler. Typically, a swirler is used to decrease axial momentum flux, and you do not want to dissipate momentum, you do not want to. So, essentially it is there to decrease the axial momentum flux and increase the swirl momentum flux. Okay. So, this air swirler causes the air coming out of these passages to take on a swirling velocity field and is now allowed to come directly impact this spilling film. So, if you will, this is a liquid film, this liquid film that is spilling over from this point here is impacted by this high speed air. This impacting by high speed air is primarily responsible for atomization. So, it is typically a design like this will operate at the liquid supply pressures on the order of less than 1/10 of a bar. So, it is very low liquid supply pressures. The liquid supply pressure is only intended to sort of push the liquid through. It is not a source of energy for the atomization itself. The atomization is entirely being controlled by the air stream. Okay. And so, this is the region where the air coming out of this swirler, the swirling air and the liquid film that is spilling over from the tip come in contact. And so, this is where you start to form a spray here. This is one design of what is called an external mix air assist atomizer. The second is where it is sort of similar, except the air is now more directly injected directly onto the liquid film itself. So, if this is the liquid film that is going to be spilling over, the air coming out is more directly impacting the liquid sheet. That gives you a different kind of a spray. Okay. Now, as you can probably imagine, this is going to give you a much more narrow spray than in the previous instance, where I had swirling air that is coming in at some angle like that. The third design is where the air and the liquid film. So, this is the air part and this is the liquid film that is now spilling over. the relationship between the air and the liquid film is much more congenial. They coexist for a little while, and it is only by the shearing action that the atomization takes place. So, the objective of a design like this is also, so the air here is serving two purposes, unlike the previous two instances. It is serving the purpose of atomization, but it is also shaping the spray. We will see what this means in just a moment. Because you have the air outside, by controlling this angle, I can control the spray angle itself, the angle over which all the drops are going to be distributed. So, this gives me an independent control parameter. In these two designs, it is hard to do that. In the first and the second design, it is hard to control the spray angle using the air. Usually, there is another source of air that may be required. Okay. So, these are all configurations called air assist atomizers, and specifically they are called external mixing air assist atomizer, because you have a simplex nozzle, and outside the simplex nozzle you have created an air passage that would cause further atomization, and you are now using the simplex nozzle only to introduce fluid into a certain geographical region, into a certain spatial region. So, in all these in these designs that use air, like we said, air is the source of the atomization energy, and more specifically we will see later on that it is the relative velocity between the air and the liquid that controls the atomization quality. So, I would rather not have a high speed liquid flow. I want to slow it down as much as possible, but increase the air velocity to where I am able to achieve the required atomization quality. Only problem with making the liquid flow rate is also independently controlled by the liquid velocity. So, I cannot independently vary the liquid velocity without changing the liquid flow rate in this kind of a design. So, for a given flow rate, I can choose an air velocity and therefore, an air flow rate that is sufficient to achieve a certain level of atomization. So, I first fix the liquid flow rate, and based on that we choose the air flow rate that is required to completely atomize this fluid. Now, in all the three previous designs that we saw, where you look at a typical simplex nozzle or even a flat fan spray flood nozzle, you are injecting into stationary air, and the spray angle as well as the drop size are fluid mechanically controlled by the inertia in the liquid itself. Okay. So, the number of design parameters that you need to control these two qualities are provided by the tangential offset. So, how far away from the center line is the tangential orifice, that is going to so in some sense control the swirl momentum, and the second is the size and number of those holes. Those are usually the two parameters that you can control to affect the flow rate and the spray quality independently. Now, as far as the spray angle is concerned, there are some interesting ways of being able to control the spray angle. One of the simplest ways is where, let us say, I take a swirl nozzle that has got a set of tangential holes just like that. I show this hole to show that it is a tangential hole. So, that creates a certain swirl action inside the spray nozzle, and by shaping this exit passage appropriately, I can control the angle over which the liquid film will depart. So, this versus if the spray was, if the passage was only sort of like that, then I would get a spray that is slightly narrower in the spray angle. So, by shaping the exit geometry of the simplex spray nozzle, one can control the actual spray angle. Okay. So, quickly, just to recap the different designs that we looked at today, we looked at the swirl atomizer in some more detail. And looked at a couple of different flat spray nozzle designs in terms of the flood nozzle and the fan spray nozzle. We also looked at spill return, and then finally, we started to look at air assist atomization. Okay. We will continue this discussion in the next class.